next step is we run to the building and come up and we're on the roof with the medium pressure. And a lot of times the kitchen's going to be, this is a single, I just boxed it out so you could see it. If it jogs up, then you've got to watch the elevation changes in Revit or even AutoCAD, looking at sections. One thing we don't want to do is position these vertical lines to where they see them from the front. On this school, it's going to be easy to hide these back here. So really all you do is go up and over, you know, the parapets, and you try to route it in such a way that, see, we're going to come over here and put a cap on it, put a gas valve there. And we're going to run over and put a gas valve there and a cap. And we'll size this line to accommodate this 200 and the future expansion. Okay, the red is medium pressure all the way back to the gas meter, and then I'm going to use a different color for low pressure. And so what we try to do is keep same size units on the gas regulator up to, let's say, 6. We used to do whole classroom wings on a gas regulator, and I don't know, it didn't seem to be a problem. But what we try to do now is set a gas regulator and pipe them to no more than 6, maybe 7. And we jump over that, go here. And you've got to look at and see where the gas tie-in is on the rooftop. And you can determine that on the family, the rooftop family. And so the gas regulator has to be no closer than 10 foot to the outside air intake on the rooftop, because they burp gas. You know, they just burp gas. That's how they work. So we got to make sure that wherever the intakes are on these rooftops, we're maintaining 10 foot from that. So when you locate your gas regulator, we're going to look at this table now. This is less than a pound. And you determine what's your longest run. I can easily say that 100 foot would work for this easily, and maybe 50 foot. But I'd go ahead and use 100 foot. You're starting here, and this is probably the longest run right there. So let's say if that's 60 foot times 1.5, we're at 90, so 100 foot. You want to round up. And if we've got 1, 2, 3, 4, 5, 6, that's what? 6 times 60 is 360 CFH, 100 feet. And you just come down and see there's 380, so 1.25 inches. So 1.25 inches leaving this gas regulator is what we would use. And then it just drops down as your CFH drops down on the 100 CFH. So 1 inch will serve up to 173, and we don't go smaller than 1 inch. 1 inch is the smallest gas that we go to. Now you've got to coordinate these bigger units to make sure that you're not, condensate's critical. Drain lines cannot be smaller than the actual tie-in. So if it's 1.25 inches here on a condensate, I change systems, you can't reduce it and go 1 inch. Gas you can if the table's saying it's okay, but we don't go smaller than 1 inch. Even if it's a 3/4 on a rooftop, we still run a 1 inch, and they just reduce it down. Does that make sense? You're basically sizing it the same way. We accumulated all the load for the 3 inch here, and then once we locate the gas regulators, then you're going to use the same longest run to size this medium pressure line from this regulator to that regulator based on 360. So 360 using 1500, it's 1.25 inches. It's 1.25 inches. So this would be actually, yeah, we did it there because, well, we got to add in the future edition.
I didn't fully follow what you were saying about the vents on the RTUs and where you place the regulator, because they burnt gas. You wanted the regulator at least
10 foot radius.
away.
10 foot radius from the gas regulator and the outside. In other words, you're okay with this one. You're okay with that one. These two are gonna be in question.
Perfect, so
Yeah.
that they are not intaking gas that's coming
Right.
from the regulator.
That's correct.
Got it.
So when we're sizing this line here, we've got to take into account the 10,000 square foot times our 51.5 B2H. So that's that's 500,000. Yeah, 500,000. So this line's going to be 500,000 plus 360, and at 1,500, so it's going to be an inch and a half. This will be an inch and a half, and then it'll be an inch and a quarter to this regulator, and then we'd size this for the future. So it makes sense. It's pretty straightforward, because all you're doing is just dropping off your load. You start it with, including the future load, 5,000 CFH, and you're just dropping it off, and see how the line size changes. Versus if we were to come in over here, it would have stayed large longer. It's still going to get smaller, but it's going to stay large longer if you went this way, because most of your load's right here because of the generator. And the generator gets its own gas regulator. Cooking gets its own gas regulator. Water heater gets its own gas regulator. And then the 200 rooftop, 200,000 B2H rooftop would get its own gas regulator, and then we would group the smaller rooftops together up to 6, maybe 7.
You said 200 gets its own and then on down.
Yeah, because when these guys fire up, if you put that 60 on there, this is going to lock out on low pressure cutoff, because it's going to be starving. If you put a regulator right here and went to there and this guy fired up, it's going to shut this one off. They're going to have to manually reset the gas valve. But these are equal in size, so it's not like they're being affected as much as this is compared to that.
What would happen in an instance where the future edition calls for you to size up larger, but what you have existing is sized down? So our example, we got almost, with the future editions, almost to that next level where we needed to size up the.
Okay, so we're at 5 million and the 3-inch can only handle 6 million.
Yeah, so when there's a disparity, and it's like what you have existing calls for, a 3-inch, but the future editions may call for a 4-inch.
That might be where we come in and say, well, this is a conservative table, and I can show y'all the comparison between this table and the 3.5 PSI drop. What it's allowing you to do is flow more load through a 3-inch on the 3.5 PSI drop than this table, because it's leaving you with less PSI at the end, versus this one's leaving you 4.5 PSI. It's leaving you 1.5 on the other table with a higher pressure drop, but you can flow more.
Yeah, so you would not want to size up your main because it may less pressure, be more expensive to the owner.
Well, it's going to be more expensive. I mean, it's going to help you in the long run. It'd give you more capability in the future if you had a larger line. But yeah, it's going to be expensive.
Okay.
Yeah. It's going to cost more. I mean, we've looked at that on projects where we come up with a 6-inch line based on on this conservative table, and compared it to the 3.5 PSI drop table, and we're able to drop the line size maybe from a 6 to a 4 on big high schools like Highland Park High School. I'm hoping this is enough to where we can sit down and actually do a roof plan or a gas plan, and then it makes sense. And then we went over, when you look at a gas generator and you look at the loads, it's going to say 50%, 75%, 90%, 100%. We want the 100%, because they're going to run it and test it at 100%. And so that's why we want, and then we have a special gas detail that we use for generators that requires at least 10 foot, 2 to 2.5. In other words, if we size this for 100 foot at 2,000, it'd be a 3-inch line that we have to on the low pressure side, leaving the gas regulator. So we want it to be 6 inches for 10 feet for that size generator, because we've experienced the same thing that we've experienced if we put these two together. They can't run it at 100% because there's not enough volume. And so we've gone back and modified our detail for that so that we guarantee that we have enough volumes, but we got to make sure that that detail's on the drawings. Okay. That's about all I had for today. I feel like it's going to be enough to where we can sit down and go to the next step and start doing some layouts and do a good job of sizing gas systems. Thank you. Pick my nose, edit that out.